For the tricep pushdown exercise, begin with your arm bent and elbow tucked in towards your side. Stand up tall and keep your shoulders pushing down. Grab the resistance band with your elbow bent or in a flexed position. With your hand grasping the band firmly, straighten your elbow into elbow extension, overcoming the force of the resistance band. Fully extend the elbow, creating a contraction of the triceps muscle. Keep the upper arm and shoulder stable and unmoving throughout the exercise. This is an open chain exercise. The osteokinematics of the joint include that it is a hinge joint, formed by the trochlear notch of the proximal ulna articulating with the distal trochlea of the humerus on the anterior side. Additionally, the olecranon of the ulna fits into the olecranon fossa on the posterior side of the humerus. The head of the radius also articulates with the capitulum of the humerus. The arthrokinematics of the joint include that the ulna is the concave segment moving on the convex humerus. Therefore, the ulna will roll and glide both posteriorly for the concentric movement. The overall torque for the movement during the concentric phase is clockwise, due to the muscle force pulling up on the segment near the axis of rotation. The overall torque for the eccentric movement is counterclockwise, due to the resistance force pulling up on the distal end of the segment. During this exercise, the external torque is highest when the elbow is flexed at 90 degrees, because that creates the largest resistance force moment arm, and lowest at full elbow extension, or 180 degrees, due to the shortest length of the resistance moment arm.
Alright, now we're going to examine our free body diagram of the cable pushdown exercise. We've frozen the movement at this position of 90 degrees of elbow flexion, so our segment here is the forearm hand segment. Just to get us oriented here, the forearm hand segment is parallel to the floor, the elbow joint is on the left, the hand is on the right, so the humerus would be perpendicular to our segment here, above the elbow joint going straight up. Our XY plane is set up so that the x-axis is parallel to our segment and the y-axis is perpendicular to it. Positive x is to the right and positive y is pointing up. Like I said, we're frozen at 90 degrees of elbow flexion, so the first assumption we're making is that we're in static equilibrium. At this instant, all forces and torques acting on our segment are equal to 0. We're also assuming our segment is rigid, meaning we can apply the laws of rigid body mechanics. We're assuming that motion is in a single plane, which is why we can perform a two-dimensional analysis, and we're also making the assumption that any force produced by muscle in this situation is combined into our one vector, our one muscle force, which is also the effort force. Alright, let's get into our forces here. We have our muscle force or effort force, labeled M, pulling straight up from the attachment point of the triceps near the elbow joint, which is our axis of rotation. M has the largest magnitude and the shortest moment arm, which is just the distance from the triceps point of attachment to the elbow joint. You'll notice that's kind of an inverse relationship because M does have the shortest moment arm. It has to have a larger magnitude than the resistance force to counteract the torque caused by the resistance force, since the resistance force has a longer moment arm. I'll explain the resistance force more in detail in a moment. We also have the force of gravity, pointing straight down from the center of our segment, indicating that there's the force of gravity acting on the weight of the forearm hand segment, so it's drawn approximately in the middle of the segment, where its center of mass would be. Gravity has a minimal effect, so the arrow is the smallest, representing the smallest magnitude. Its moment arm is from that point of application in the center of the segment to the axis of rotation, the elbow joint. Coming back to our resistance force labeled R, which is pulling straight up on the hand end of our forearm hand segment, since the hand is holding the resistance band and that's where the tension is. The resistance force has a moment arm from its point of application at the end of the segment to the elbow joint at the other end of the segment, so the longest moment arm. Our last force here is the joint reaction force, which we've drawn equal and opposite our largest force in the diagram, which in this case is the muscle force. The muscle force pulls the ulna up against the humerus, so the joint reaction force is really the force of the humerus pushing back down on the ulna, equal and opposite the muscle force. The joint reaction force is pointing straight into the joint, so it doesn't have a moment arm. Of our forces, the muscle force and joint reaction force are both internal, since the muscle force is generated by the triceps muscle and the joint reaction force is generated by the humerus pushing back down on the ulna. The force of gravity and the resistance force are both external, caused by outside sources, in this case, gravity and the resistance band. Since all forces we've drawn are along the y-axis of our plane, there are no x components to take into account or component vectors to break apart. That's why we drew the joint reaction force with purely a y component. Because our muscle force and resistance force are on opposite sides of our axis of rotation there in the center, this makes it act as a first-class lever, which is a rare example in the human body. In order to make this exercise more difficult, you could increase the weight of resistance by using a stronger band, or if you're doing it on a cable machine, by adding more weight to the stack. Increasing the resistance force increases the torque that's trying to act in a counterclockwise direction, so the muscle force would have to increase in order to balance that out and actually move the segment in the clockwise direction that you want it to go in order to complete the exercise. You could also grab a point higher up on the resistance band to increase the tension in the band, which has the same effect as using a stronger band. In order to decrease compressive forces, like for a patient with arthritis, you could decrease the weight of the resistance force by using a smaller band, grabbing a point down lower on the band itself, or decreasing the weight stack if you're using a cable machine. This would decrease the amount of muscle force you have to produce in order to counteract the torque caused by the resistance force. And since we've drawn our joint reaction force equal and opposite to the muscle force, decreasing the muscle force would decrease the compressive joint reaction force, allowing for less compression in that elbow joint between the humerus and ulna. We will address shear later on in our project, and for now, that's our analysis of the tricep push-down exercise.
When doing a push-up, you want to begin with your hands on the floor directly under your shoulders in plank position. Keep your feet together and try to keep your back as level as possible while also keeping your core tight. Once you're ready, bend your elbows until you reach at least 90 degrees, bringing your body closer to the floor. Then extend your arm up, bringing your body back up to starting position. Because your hands are in a fixed place on the ground when doing a push-up, this exercise is a closed chain exercise. As for the osteokinematics of this exercise, at the elbow, the trochlear notch of the proximal ulna articulates with the trochlea of the humerus on the anterior side. The olecranon of the ulna fits into the olecranon fossa on the posterior side of the humerus. The head of the radius also articulates with the capitulum of the humerus. As for the arthrokinematics, the elbow is a hinge joint that allows for both flexion and extension. With the forearm as the stationary segment, the humerus is the convex part moving on the ulna, the concave portion. Therefore, the humerus will roll posteriorly and glide anteriorly when the arm is being extended in the push-up. External torque is highest at the bottom of the push-up because gravity has the highest moment arm in that position. External torque is lowest when the arm is fully extended because gravity has its lowest moment arm in that position.
Alright, now we're going to get into the free body diagram analysis of our push-up exercise. We're making the same assumptions here as in our other exercises, that our segment is in static equilibrium, meaning all of our forces and torques are equal to 0 at this instant. Our segments are also rigid, so we can apply the laws of rigid body mechanics. Our motion is in a single plane, so we'll be performing a two-dimensional analysis, and any forces caused by muscle will be combined into one single vector, denoted as the muscle or effort force. Okay, so our segment drawn here is the upper arm. The left side is the end of the humerus that articulates with the shoulder joint, and the right side of the segment is the elbow joint. So our elbow is bent at 90 degrees, and the forearm is perpendicular to the ground, palm flat on the ground. This is the down position of the push-up, where you end the eccentric movement and begin the concentric movement. Our XY plane is set up so that the x-axis is parallel to the upper arm, positive direction is to the right, and the y-axis is perpendicular to our upper arm segment, positive direction pointing up. Into forces now. Our muscle force here is still that of the triceps, but as it's contracting, it's pulling along the upper arm horizontally from its point of insertion at the olecranon. The muscle force is the largest force magnitude, but again has a small moment arm, only the short distance from the attachment point of the triceps to the axis of rotation, the elbow joint. We have gravity again pointing downwards from the center of mass of our segment, which has a pretty small magnitude. Its moment arm is the distance from that point of application in the middle of the segment to the axis of rotation at the elbow joint. So the moment arm here is greater than the moment arm of the muscle force. In a push-up, our contact points are our two hands and our 2 feet. So looking at just this diagram, our weight is pushing down to the ground through the hand. That means that there's an equal and opposite ground reaction force pushing back up through the hand and forearm. That ground reaction force, however, isn't directly touching our upper arm segment, but it's acting through the forearm, which is going to push on the humerus. So we've labeled this force the forearm on humerus force, which is really how the humerus perceives the ground reaction force. This force has a magnitude less than that of the muscle force or effort force, but greater than that of the gravity force. It has no moment arm since it's acting directly on our axis of rotation. Our last force here is the joint reaction force, which we've drawn going directly into the joint from the upper left, or what would be quadrant 4 in our cardinal plane. We did this because the joint reaction force opposes the other forces that are acting on the joint. The muscle force is acting on the negative x direction, and we're going to subtract the force of gravity from the forearm on humerus force, since both are y vectors but opposite. Since the forearm on humerus force has a larger magnitude than the force of gravity, that leaves us with a force in the positive y direction. Combining that with the direction of the muscle force would give us a combined resultant force in the negative x and positive y direction. So we've drawn our joint reaction force acting opposite that, in the positive y and negative x direction. The magnitude of the joint reaction force is determined by breaking it into components. The y component of the joint reaction force would be equal and opposite that of the forearm on humerus force minus that of the force of gravity, and the x component of the joint reaction force would be equal and opposite the muscle force. The joint reaction force has no moment arm since it's pointing directly into the joint, which is the axis of rotation. Our joint reaction force, along with our muscle force and forearm on humerus force, are all internal. Forearm on humerus force coming from the forearm pushing on the humerus, joint reaction force coming from the humerus pushing back on the ulna or forearm, and the muscle force coming from the contraction of the triceps. The only external force in our diagram is the force of gravity. In this exercise, we're still working as a first-class lever, since opposing forces are on opposite sides of the fulcrum. Elbow extension is one of the rare examples of a first-class lever in the human body. In order to make this exercise more difficult, you could increase the weight of the person, or more realistically, increase their load, like by adding a plate or other heavy objects to their back. This would increase the ground reaction force and therefore the forearm on humerus force, so we would have to increase our muscle force in order to counteract the torque caused by the resistance at the joint. In order to decrease compressive forces, like for someone with arthritis, you could elevate both hands on a platform, which increases the weight you put through your feet and decreases the weight you put through your hands. With less of a forearm on humerus force, you wouldn't have to have as big of a muscle force in order to perform the movement. You could also perform the push-up on your knees instead of the standard method, which decreases the load by taking away the weight of your lower legs. Less load means less weight put through your hands, less of a forearm on humerus force, and less muscle force required to counteract the torque. This decreases the joint reaction force, decreasing the compression at the joint. And we'll address shear forces at the end of our project. And that is our analysis of the push-up diagram.
For a tricep kickback, begin with the elbow flexed at approximately 90 degrees with the dumbbell in your hand. Fix the position of the shoulder and the wrist and begin moving the elbow into extension. Once reaching full extension, a slight pause is taken before the elbow returns to the starting position in a controlled fashion. For osteokinematics, at the elbow, the trochlear notch of the proximal ulna articulates with the distal trochlea of the humerus on the anterior side. The olecranon of the ulna fits into the olecranon fossa on the posterior side of the humerus. The head of the radius also articulates with the capitulum of the humerus. For arthrokinematics, the elbow is a hinged joint that allows for flexion and extension. The ulna is the concave segment moving on the stationary convex humerus. Therefore, the roll and slide of the ulna will both occur posteriorly towards the back in the orientation of the exercise. Because your hands are not in a fixed place and are freely moving when doing a tricep kickback, this exercise is an open chain exercise. External torque is the highest at full extension and is lowest at the starting position or 90 degrees because the weight in the hand has a higher moment arm in extension.
In our free body diagram for the tricep kickback, we are assuming that the elbow is flexed at 90 degrees, allowing the forearm segment to be parallel to the force of gravity and perpendicular to the floor. We are also assuming our segment is rigid and the movement is happening all in the sagittal plane, meaning that we are doing a two-dimensional analysis. Our final assumption is that all muscle and effort force is combined into one single vector. Our segment of interest for this exercise is the forearm segment with an axis of rotation at the elbow. Our free body diagram is oriented with the x-axis moving inferiorly and the y-axis moving posteriorly. The forces present in this position are the weight of the dumbbell in the hand, the force of gravity on the forearm, the muscular force produced by the triceps brachii, and the joint reaction force at the elbow. The weight of both the dumbbell and forearm work directly inferior and pull the segment towards the ground. The muscular force is applied to the insertion of the triceps brachii, the olecranon process, and pulls superiorly. Due to the static nature of this position, the joint reaction force will resolve our other three forces, thus it is being applied in the elbow joint at an angle so as to equal the y component of the gravity and weight and the x component of the muscle force for a sum of torques equal to 0 Newton meters. The anatomical features of the elbow create a first-class lever. The anatomy also causes the moment arm of the muscle force to be the shortest, while the moment arm of the dumbbell is the longest. The relationship between the magnitudes of our forces is simply the inverse of the moment arm relationship, as the muscular force must be the largest in order to produce a torque equal to the torque produced by the force of the weight in its longer moment arm. It should be mentioned that in this position, due to the weight being directly inferior to our axis of rotation, no torque is actually being produced by the dumbbell, and that this relationship exists during all of the phases of the exercise. Our external forces are gravity and the weight of the dumbbell, while our internal forces are the muscle and joint reaction forces. To make this exercise more difficult, we would add a larger weight in the hand, thus increasing the force of the weight and in turn the torque it produces during the movement. To decrease the compressive forces, we want to decrease the total joint reaction force. In order to do this, we can decrease either the weight in the hand or the moment arm of the weight by moving it up in the forearm towards the elbow. This will reduce the torque created by the weight, meaning the triceps will not need to produce as much force, which in turn reduces the joint reaction forces, reducing compression of the joint.
For the elbow joint, because of the bony anatomy and how the olecranon of the ulna cups around the humerus, shear forces are minimal and mainly caused by varus and valgus forces. Therefore, for all three exercises shown, any stabilization to the elbow joint will help diminish shear forces. For example, keeping the humerus and ulna in the same plane of movement, avoiding excessive loads, using proper musculature and core stabilization, proper form, and supervision to correct the form if needed.